Great. Hi, everyone. Well, this was a little bit of a strange logistical story because this event was on my calendar for yesterday. So I showed up at this time yesterday, and I was very pleased to find here my great friends, Rule 54 and Rule 110, being the subject of the conversation. So that was terrific. And in general, it's wonderful to see all this work that's being done on cellular automata and Turing machines, and some of my lifelong very best friends. Well, so what I want to do today was talk a little bit about the general field of exploring the computational universe, but then I wanted to tell you about a very unexpected discovery that I kind of started making about 30 years ago, but really made in the last year or so. That kind of gives us a new way to kind of a new story about using kind of ideas like cellular automata, but not really cellular automata, using kind of the core ideas of the computational universe to crack a kind of a Mount Everest of science, the problem of finding the fundamental theory of physics. And we've made, frankly, spectacular progress. And I think it's very clear that at very least we're climbing the right mountain to get to the fundamental theory of physics. And it's very much using the kinds of ideas that I think you all have been interested in exploring and studying the computational universe. So before I talk about that, let me make a few comments about the general landscape of cellular automata and their friends. So the thing that, in a sense, is most amazing to me about cellular automata is even among the elementary cellular automata, the 256 things that I started studying back in 1981 or something like this, that there are still things to figure out. And there are still questions. Within the last few weeks, I kind of ended up studying something that I can't believe I never looked at before, to do with the elementary cellular automata. So the first thing is there's still so much more to figure out, even about the elementary cellular automata, and it's terrific to see people at this conference studying those kinds of things. That's the first point, that this is a very deep and rich field. And even even the things right close to the starting gate, we haven't finished mining. Second thing to say is something that's become clear to me over the basically close to 40 years now that I've been interested in and working on things like very simple cellular automata. The following fact, that any sufficiently simple model winds up being important. And we've seen that, for example, with the elementary cellular automata. We see that, and you know, I used to actually have file folders for each of the elementary rules. They're not physical file folders anymore, where I would put, you know, papers that I would see about Rule 4, Rule 184, for example, Rule 54, all these kinds of things. And almost every one of those elementary rules has ended up finding interesting applications or interesting pieces of essentially mathematical science to be done about them. So I think one of the principles that's really worthwhile to bear in mind is if you study a sufficiently simple program, a sufficiently simple model in the computational universe, it will end up having applications in the future. The more complicated it is, the less likely it is that the thing you study will specifically be something that ends up having applications. Well, so what is the sort of bigger picture of this study of the computational universe? You know, I got interested in this around 1980, 1981. I was kind of interested. I'd been doing traditional particle physics and cosmology and things like that. And I had tried to use those methods to kind of study what seemed to be fundamental questions in science about how complexity arises and things like that. And I kind of realized that the methods and models that I had been using were sort of not general enough and not correctly oriented to be able to deal with the things I was interested in studying. So I started thinking, what are some new primitives that could be used to make models of things? And so I quickly ended up coming up with what ended up what I decided to name in sort of honor of their two-dimensional friends, cellular automata, one-dimensional cellular automata. I think that the thing that was, for me, kind of a difference in methodology from what I had been used to doing in physics and in sort of traditional natural science. It's like you're throwing a bunch of phenomena in the world and you're asked to sort of reverse engineer those things and go find how they might work underneath. What I started doing at that time was just saying, let's explore this abstract universe of possible simple programs and see what they do, and see whether the things that they do correspond to things that turn out to happen in nature, and so on. And of course, the answer is yes, they do correspond to lots of things that we see in nature. But most importantly and methodologically, they gave us sort of new building blocks for making science and making theories in science out of. And the key methodology in studying this computational universe of simple programs is, at least for me, doing computer experiments. I actually now, and I'll talk a little bit about this maybe towards the end, a very recent thing in the last few weeks actually has been a study of essentially the physicalization of metamathematics. And I think I finally understand in some fundamental way why computer experiments will always give you more diversity and more success in exploring kind of the universe of possibilities than traditional mathematics. I think I finally have an actual kind of way to understand that at a scientific level, which is kind of cool. But in any case, so for me, it's like doing computer experiments, and and for me, it's kind of like you do the basic experiment. I don't know. Let me. I gotta. When in doubt, interact with one's computer here. So let's say, I've got, let's make this a bit bigger. It's got so much easier to do this in the intervening years, but I can say, one of my all-time favorites is Rule 30. But let's do the following. Let's say we just do this sort of original experiment that I did back in 1981 or so, of just let's look at the elementary cellular automata and let's start them off, let's say, with single cell initial conditions, and let's just say, what do they do? Let's just do all of our friends. And here are the results. And this is sort of a typical exploration of the computational universe. What kinds of things happen here? And we see the nested patterns and so on. And then turning our sort of telescope in this direction, we see Rule 30. And we see, starting off from that simple initial condition, we see this behavior, and Rule 30 has been, for example, a pseudo-random generator that we've used in Wolfram language for years. Actually, it was recently retired in favor of a slightly more efficient cellular automaton, but it has served well in that capacity. And in a sense, what we sort of the big surprise here is that in the sort of computational universe of possibilities, that we see such rich behavior and we get to it so easily. And in a sense, that observation is the fact that in this sort of computational universe, we see this phenomenon of being able to generate complexity easily. That, I think, is a very core scientific phenomenon. And if I'm, to give historical analogs of these kinds of things, it's like the things we've discovered here are kind of like what, Galileo found in 1608 when he pointed his telescope at the sky and saw the moons of Jupiter. And that discovery made progressively led to the development of kind of mathematically oriented science and the realization that that idea of sort of mathematical models was going to work in a fairly global context. What we're seeing when we look in the computational universe is a different kind of unexpected phenomenon, this phenomenon that even though we may have simple rules, we get very complicated behavior. And that's sort of a core phenomenon. And what I think we will see over the years, and we've seen it developing quite nicely in the last few decades, is kind of the development of a kind of science that's based on those ideas, those computational ideas, as their kind of core founding principles, much as the mathematical sciences have been based on kind of the idea of mathematical equations as their core founding principles. And I think one of the things that one of the questions is we go explore the computational universe. We find all these kinds of remarkable things happening out there. What kinds of general principles can we discover about the computational universe, which we can then apply to other things? The biggest principle, as far as I'm concerned, is this, what I call principle of computational equivalence. The idea that if we think about the processes going on in these simple programs as computations, that the sophistication of the computations that happen in these programs, as soon as the behavior is not sort of obviously simple, the behavior will be of equivalent computational sophistication. And that principle of computational equivalence, I'm pretty sure is a pretty core principle that's going to weave its way both through science and through a lot of technology and through a lot of thinking about things in general. And we've already started to see plenty of this happen over the years. But I think this principle has a very long way to go. And it's a principle like many other principles, like, I don't know, the second law of thermodynamics, things like that, which, by the way, is closely related to principle of computational equivalence and follows in the end from it. It's a complicated thing because it's both at some level a definition, it's at some level a mathematically provable result, at some level it's sort of a law of nature. It's a combination of those things. We can talk about kind of the epistemology of it, which is an interesting thing. But at a practical level, it's a guide to a lot of things that we see in the computational universe, and it has various predictions. Like it says, you know, when we look at these different kinds of systems, as soon as we see not obviously simple behavior, we will see behavior that turns out to be computation universal. And we're steadily getting more and more evidence about this. And, you know, for example, a dozen years ago now, we did this Turing machine prize for a little Turing machine that I had found was the simplest conceivably universal Turing machine. And yes, you know, it is true. It is in fact universal, as the principle of computational equivalence would lead us to expect. And this sort of search for the frontier of universality is something that I actually intend to reinvigorate a bit in coming times. I should say, in terms of, let's see, now I'm realizing I didn't put this up here. Okay. Actually, what I want is that page. Here we go. So, you know, this is sort of highlighting, this is a prize that I put up last year. This is kind of highlighting how much we still don't know, even about simple cellular automata. This is about Rule 30. And I don't know whether this prize, unlike the Turing machine prize, which got resolved in 6 months, I don't know whether this prize will be a Fermat's last theorem kind of thing that takes centuries to resolve, or whether it will be something that happens more quickly. But I think it's remarkable that we're still at the point where these are questions that have to be asked. In any case, I think one of the things we learn from the principle of computational equivalence is this idea that the frontier of universality will be close at hand. And there are some very interesting examples that I've actually been studying very recently about that in different kinds of systems. So another thing that we learn from principle of computational equivalence is the idea of computational irreducibility. The idea that although we can just go through and follow each step in the evolution of a system like this, there will in general be no way to kind of jump forward and see what the system is going to do much more efficiently than the system itself does it. And this idea of computational irreducibility has so many consequences in different places. And the ubiquity of it that's suggested by the principle of computational equivalence is really an important one. I mean, one consequence of computational irreducibility, it's sort of an explanation of why we see so much complexity in the world. It's because in all cases, the system is doing something to compute how it will behave, and we, as observers of the system, are sort of doing our best to outrun the system and figure out what it's going to do and be able to sort of crush the actual computational process that the system is following. But the principle of computational equivalence and computational irreducibility means we in general can't expect to do that, and that's why these systems seem to us so complex. But there are just so many consequences to computational irreducibility. I mean, I was somewhat amused. Last year, I ended up giving some testimony for the US Senate about AI-based systems for selecting content on the internet, basically the big tech companies and what they do. One of the things that comes up there is, can you just like look at the algorithm and figure out immediately what's going to happen? And the core reason you can't do that is because of computational irreducibility. So I was kind of pleased to see it actually make its way into the congressional record and so on, the concept of computational irreducibility. I have found that people in general seem to get the concept more easily than one might think. I mean, historically, it was not an easy concept to communicate, but it turns out that I think perhaps in modern times with experience with computers, people do seem to get this concept. And in time, just as we have seen from the early days of kind of mathematical sciences, ideas like energy and momentum and so on, ideas that are core to sort of the mathematical approach to science, eventually make their way into our thinking about things in general. So in time, we will certainly see things like computational irreducibility make their way into thinking about things in general, whether it's AI ethics, or whether it's kind of the limits of predictability in science or the limits of what science can be expected to do. There's been kind of a long run where everybody thinks science can just figure out everything. That's something of relevance in this pandemic, for example. But computational irreducibility kind of shows one from sort of within science some of the limitations of science. And I think that's a pretty interesting thing. It also tells us it's both an expression of the limitations of science and an expression of things like why issues like it sort of relates also to more philosophical issues about free will and when you can still have a deterministic system, but nevertheless what it does may be unpredictable to anything outside. And it also sort of tells us that it kind of gives us a thing that's being achieved by the passage of time. While I have this on the screen, I'll show you, that wasn't what I was going to show you. I was going to show you, oh, here we go. I was going to show you the thing that I happened to run across with Cellular Automata just recently. This is something I may talk about later. This is the thing we call rule space, which is a kind of generalized universe of all possible universes that also gives us some new insights into things like the P versus NP problem in computational complexity theory. But there's sort of a feature of kind of determinism versus non-determinism in Cellular Automata. And I couldn't believe I'd never made this picture before. In any case, this is sort of a representation of how different elementary rules kind of unpack from each other in this kind of rule space. All right. So I just want to say that, when we look at the kind of the computational universe and we see all the different things that happen, there's kind of a question of what we can make from this. One of the important things is what I might call mining the computational universe for things that are useful for human technology. So for example, Rule 30 is useful as a random number generator. Many other things that we can mine from the computational universe are useful for many different particular human purposes. And sometimes the main challenge is to understand the purpose, and then we can go off and mine for it, so to speak. A good example of where that happens a lot is in machine learning and in neural networks and so on, where we're dealing with systems vastly more complicated than the kinds of things that I think we've studied mostly in the computational universe, but where we can see that by taking those systems, we can adapt them to serve useful purposes from the examples we've given and so on. Now, one thing to understand, and we've done some experiments on this, we have a great framework for dealing with neural nets in Wolfram language. And so there's sort of the question of to what extent can we merge what we've learned from the computational universe with what we learn from kind of the adaptive behavior of complicated neural nets. I think one of the key things from the computational universe is you might have thought, and this was sort of one of the big early discovery, you might have thought that you needed this big complicated system in order to get behavior that's interesting, so to speak, but you don't. It's sufficient to have these very simple programs to get very complicated behavior, and that's something that in time I think will merge with what we've learnt from doing this kind of adaptive tweaking of these very complicated programs. Well, so as I say, there's this, we can think of sort of the computational universe as this vast ocean of kind of computational possibility with all kinds of things going on, whether it's Rule 30, whether it's some simple Turing machine, all kinds of things. There's all kinds of stuff going on there. The thing that, and those things are things that we should study for science. There's a lot of richness to explore there. But there's a question of, if we're going to make use of those things as humans, how do we do that? It's like when we look at the physical universe, we can mine things, we can find magnetic materials, we can find liquid crystals, we can find uses for those things that fit in with our human purposes. So similarly, in the sort of ocean of computational possibility out there, how do we systematically find the things that are useful for our particular purposes? And I guess in addition to studying the computational universe, my other kind of lifelong pursuit has been the development of computational language to be able to, as I see it, form a bridge between the kinds of things we humans want to think about and talk about and the things that are possible in this computational universe of possibilities. And so, as I'm sure most of you know, a large part of my life has been devoted to building our Wolfram language system, whose purpose is really to be able to have a language that can express ideas computationally about lots of kinds of things. And it's something which is really a different objective than, for example, people have had in traditional programming languages and so on. The objective is to actually take things that we would think about and express them computationally so that they can be for two purposes. One purpose is so we can explain them to a computer, and another purpose is so we can kind of crispen up our own computational thoughts. I mean, kind of I view our activity as being an analogous activity to the activity that happened maybe 400 years ago when people invented notation for mathematics. I mean, before 400 years ago or so, if you wanted to describe mathematics, you mostly did it in words. Then things like plus signs and equal signs and so on were invented, and that made for a huge streamlining in being able to actually explain things mathematically, so to speak. And in a sense, what we're trying to do is, and by the way, that sort of streamlining led to things like the invention of algebra and calculus, and basically led to the mathematical sciences as they now exist. So in a sense, what we're trying to do is to provide, similarly, a notation, a language for computational thinking. And it's a bigger, broader thing than the operations of early mathematics, so to speak. So it's a bigger task, and I've spent the last 40 years on it, so it's taken a little while. But we're at the point now where we can express an awful lot of things, whether it's about, about chemistry or about food or about whatever else, or about different kinds of operations and algorithms. We can express those in a precise symbolic computational language, which is both understandable by humans and understandable by machine. And I think one of the things that actually should be kind of a core principle of the field of studying the computational universe is create computational essays as your way to express what you're doing. Write something where it's a mixture of computational language and natural language, because that's kind of the way to most clearly express the kinds of things that you're trying to do. Just as one's mixed natural language with mathematical notation, now one can mix natural language with computational language, and that's really a great way to kind of express things in this area. But the thing that we're trying to do with computational language is provide this way to sort of provide a notation for computational thinking that can be sort of run against the sort of ocean of computational possibility that we've discovered exists in the computational universe. And the main purpose, in a sense, is to do kind of like what mathematical notation did for the mathematical sciences, to enable, in that case, it was mathematical X for various fields of science X. Now what we want to do is to sort of enable computational X for all possible fields X, from kind of archaeology to zoology and beyond. And I would say that this has been something that we have seen being very successful in recent years, and that trend will continue and no doubt accelerate in the time to come. But I think one of the things I want to say, so it's a pretty good heuristic that if you have a field X, if there isn't already a computational X, there soon will be, and it will be the future of that field. And so one of the questions then is, what is the kind of, when you think about thinking about things computationally, what extra mileage can you get that you couldn't have got before? So one of the things that was the point of like my New Kind of Science book, for instance, is this idea that by mining the computational universe for models, you have a much richer source of modeling material than you do just for mathematical equations. And it's turned out that even for about 300 years, when people were doing exact science, people had said, well, the kind of gold standard for what we do here is to make mathematical equations to describe the systems we're setting up. But what's happened in the last limited number of years is a pretty pretty total transition. When there are new models being made of things, those models are overwhelmingly computational models. They're overwhelmingly programs rather than equations. And it's kind of a dramatic thing, which I think some historians of science have started really noticing, that after 300 years of kind of mathematical equations, we have entered a period where we are transitioning very firmly to kind of the computational paradigm as the approach to science. So one of the things I wanted to point out here is when we think about kind of that approach to science, the kind of computational approach, computational X, there's a question of what is the core basic science that underlies all of that? What is the analog of pure mathematics? What is to this computational X set of fields what pure mathematics is to the mathematical sciences? And I think basically the answer is it's the kind of thing that you all do and that I like very much to do, the kind of pure basic science of the computational universe. And I have been very much interested in this field for a long time, and maybe one day there'll be a great name for that field. For me, kind of the, calling the big book a new kind of science is sort of a wimp out, but for not having to come up with the name, so to speak, for that field. But I think that the thing to understand is that it is the science of the computational universe and the pure basic science, which is what I think you guys are mostly concerned with, that is kind of the analog of pure mathematics. And as I mentioned earlier, whenever the systems you study are simple enough, it's sort of inevitable that they end up being the upstream versions of things that get used in lots of different places. Okay, well, so it's so one of the things that given this sort of paradigm, given this computational paradigm, this idea of making models for things in terms of programs, there's a question, what can you do with that? Well, I studied lots of things in biology and some physics and so on, and many people have studied lots of other kinds of systems in social science and economics and in mathematics, all kinds of places where one can use this idea of simple programs in the computational universe. But one of the places that I was curious whether this could be applied is in fundamental physics and finding an actual fundamental theory for how our universe works. And people had said, oh, we can make cellular automata that do that. I never really believed that. I always thought that cellular automata are wonderful minimal models for parallel computation once you've defined your notions of space and time. But in a sense, if you want to make a fundamental model for the whole physical universe, you kind of have to go underneath space and time. You have to go to something more fundamental than that to start understanding how the universe works. And back in the early 90s, actually, I had started exploring networks as sort of the raw material from which to make universes, so to speak. And I spent about 100 pages in NKS talking about this. I think the world was not really ready for things at that point. And I wasn't completely happy with the models I had, although, as is so often the case, they turn out to be equivalent to the models that I have now. But I needed to think about them in a different way to make more progress. But in any case, the thing that, in the end, so in a sense, the first question is there a simple model for our universe? We don't know for sure. But if there is, if we're going to package everything we know about our universe into this tiny little program, there isn't really room to put a 3 in there for the number of dimensions of space or some particular number for the mu1 electron mass ratio. Everything has to emerge from something which is a tiny program that in which all of those things are somehow implicitly bundled in. So, okay, so how might that all work? Well, as I say, the amazing thing is that we've actually figured out a lot about how this works. And in fact, it's been, I'm kind of shocked at how easy it's been. I think that, in a sense, the physics that we do today has been very much based on physics that was done about 100 years ago. The two principal thrusts of 20th century physics, both very wonderful theories, quantum field theory, quantum mechanics, and general relativity, the theory of gravity. These were invented around a little bit 1915 and the 1920s, so about 100 years ago. And they have been what have taken physics to where it is today. But they haven't given us kind of the final theory of how physics works. What we've been able to do is to find kind of a lower level machine code from which quantum mechanics and general relativity emerge, as well as a lot of other kinds of things. So let me give you kind of a rough picture of how this works, and then I'll try and talk about this in a little bit more detail. So this is kind of the big picture of kind of our model for physics. And what it's based on is, first of all, there's no notion of space and time to begin with. There are just points. You can think of them as sort of atoms of space. And these points, the only thing we are going to say about them is how they're connected to other points. We're not going to discuss embedding them in some definite space. We're just going to say these points are connected in some way to other points. And then we're going to have a rule that says, given that we have some, we can think about these points as being just elements, and we can think about these points as having relations between points. And we say, with certain forms of those relations, we will transform them into certain other forms of those relations. It's a very minimal kind of thing. We can represent that graphically. Here's an example of one of those, represented as one graph is transforming to another graph. It's more robust to think about hypergraphs, where these relations aren't necessarily binary relations, like in a graph where there are just two ends to every edge, but are generally hyper edges with arbitrary numbers of elements in each relation. But so the idea is we just have these atoms of space, these points, and these rules for transforming them. So if you run those rules for a while, you end up getting complicated, just like in cellular automata and so on. You end up getting these very complicated patterns of behavior. And the kind of the concept here is the limit of this kind of thing is the space that exists in our universe. So in a sense, if we look back sort of historically, Euclid has his first common notion is a point has no extent. In other words, you can put a point anywhere in space. You can, space is continuous. One of the fundamental ideas of this model is that that's not true. That in fact, there are discrete atoms of space. And not only that, in fact, everything in the universe is simply made up from the connectivity of these atoms of space. So all of the features of matter and particles and so on, those are features just like the localized structures of Rule 110 or something like this. And it's great that there's a group in which I can say that and people understand what I'm talking about. Those are like the way that particles emerge, particles like electrons and so on, emerge from these hypergraphs. They are sort of topological obstructions in these hypergraphs. And that's the way that things like matter and so on emerge. There's sort of a background of space, and on top of that, there are things like matter. But everything in the universe is just made of space. Okay, so here's where there's sort of a departure. So this sounds a little bit like it's something a little bit like a deterministic cellular automaton. It's got rules, et cetera, et cetera, et cetera. It doesn't happen to have its own, it builds its own notion of space rather than having that built in as a lattice. But otherwise, it's sort of following deterministic rules. Okay, here's a key difference. The key difference is these particular rules may have many places that they can be applied in the system. And the idea is to say, let's apply it in all possible places. Let's make a multi-way system. There's a section on those in the NKS book, actually. But let's make a multi-way system that represents all possible ways that those rules could get applied. Okay, and then what we're going to do, so I can explain roughly how this works. The limit of this is physical space, and I should make another point here. When we think about this, the limit of this being physical space, one of the things that if you're into physics, you may say, oh my gosh, how can this possibly be right? Is we're talking about space, but we're not yet talking about time. And in this model, space and time are very different kinds of things. Time is kind of the inexorable computational process of applying these rules. Time is sort of measured by the computationally irreducible process of going from one configuration to another. Space, on the other hand, is just the extent of this hypergraph. Now, back from the early days of relativity, people had this idea of packaging these together into space-time. It's mathematically very convenient in relativity to do that, and to think about space and time as being the same kind of thing. Yet in these models, space and time are very different kinds of things. So how can that possibly work out? Well, the answer is that if you are an observer embedded in this space, the only thing that you're actually sensitive to is essentially causal relationships between the updating events that happen. So as this network is updated, there are particular places where a particular rule will be applied. You can ask the question, what are the causal relationships between the application of these rules? Think about these rules as sort of being applying functions. It's like, were the arguments to one application of this function yet available from the output to previous applications of the function? And you can make a graph that represents a causal graph that represents that collection of causal relationships. And I maybe can show you a little bit later, but it turns out from that causal graph, you can quite quickly derive special relativity. And when you make a very important condition I call causal invariance, which again, I'll try to talk about. Let me say something about what causal invariance is right now. So let me pull up something else here. Actually, let me go back and talk a little bit about, I'm going to give you a little preview here. I'm going to say that one of the features of these multi-way systems is they basically give us quantum mechanics. And just as physical space is kind of a slicing of this causal graph that represents causal relationships between events in space and time, so the slicing of this multi-way graph, or actually more officially the multi-way causal graph, gives us this map, not in physical space, but in what we call branchial space, the space of branchings. And this map is essentially a map of quantum entanglements between states. And so in a sense, what we find is that physical space corresponds to the extent of this hypergraph. Quantum mechanics arises from this branchial space that exists as a result of this set of possibilities associated with the multi-way system. And one of the amazing and beautiful things that happens is that it's possible to derive the Einstein equations for general relativity from the behavior of these hypergraphs. And it is then you can actually derive the analog of the Einstein equations for a multi-way causal graph in branchial space. And the analog of the Einstein, what are the Einstein equations in physical space? In branchial space correspond to the core fact of quantum mechanics, the Feynman path integral. And so it turns out in this model, one of the just amazingly elegant things is that the Feynman path integral simply is the Einstein equations, but in branchial space. And that's a piece of sort of unification between quantum mechanics and general relativity. They're sort of the same theory, but operating in different spaces. And we can see the interplay between these things in, for example, black holes and so on, where essentially the branchial space and physical space get merged together in a certain way. All right, let me give a little bit more detail here. So let's say we're starting off and looking at, let me pull this up, here we go. Okay, so this might be one of the pieces of raw material that we're dealing with. This is just a set of relations between elements. We can represent that by a graph. Now we can say there's a transformation rule that says this, for any x and y, et cetera, transform it in this way. This is creating some new element W. The only thing we know here is that these elements are differently named elements can be distinct. So one of the things I should say that's sort of embarrassing to me is that this structure of looking at the sort of transformation rule for a symbolic expression, which I sort of thought of as being the new thing that I was thinking about in terms of making this model for fundamental physics, is actually for me an unbelievably old thing. It's the thing I've used to build computational languages for 40 years. But it is taken, usually when we build, if we look at Wolfram language, for example, it works by applying transformation rules to symbolic expressions. But the way it works all the time is to apply transformation rules to symbolic expressions that mean something, that have a plus in them, that have a some particular function in there. What happens here is this is the ultimate pure infrastructural form of transformation rules for symbolic expressions. There's no meaning here. It is just structural. It's just saying, take this symbolic expression and transform it this way. So it's in a sense the same thing that I've been doing for years, but it's been made more it's been desiccated to the point where it is purely the infrastructure and not the content. Now, curiously enough, for people who are interested, it turns out you can think of these models as also being a desiccated form of category theory. And actually, some of what I'll talk about is related to higher categories. We've just been understanding all of this correspondence. And one of the things that's interesting is Rullial space turns out to correspond to infinity categories, and Grothendieck's infinity groupoid makes a big appearance. And it's all rather an elegant mathematical structure. In any case, so we can represent that transformation rule as a transformation rule between, in this case, graphs. And we can start saying, well, okay, if we have a graph, let's say we start with this graph here, what happens if we just apply those rules to that graph a bunch of different times, and we'll get something like this. We can go and we can start doing the zoology of these kinds of systems. These are some of the structures that you get. Now, remember that these graphs, the only thing that's really meaningful in these graphs is the connectivity information. The particular way they're laid out is just the way the Wolfram language happened to lay out, these out on a page. There are a few more of these. So it's fairly typical to get fairly complicated behavior, even from very simple rules from these kinds of systems. Now, one question is, well, what is the limit of one of these kinds of structures when you make it very big? Well, let's look at this one here. This is a particular rule. This is a particular hypergraph rule. Let's just let it run. There it is for the first few steps. Okay, if you keep it running for a while, this is what you'll get. You'll get something which is essentially knitting a two-dimensional surface. So that's kind of interesting that you're kind of knitting something which looks like a two-dimensional flat Euclidean space. Well, we can go on, we can look at other systems here. Here's another example. This is knitting something slightly more complicated. We can maybe look at another example here. This ends up knitting this structure here, which we can render quite conveniently in 3 dimensions. So it's sort of remarkable that we can start from these very simple rules that have no notion of space, and we can end up with these structures that look like they are forming things like manifolds, in this case a manifold with curvature. Well, so a question might be, can we characterize from the underlying connectivity information, can we say, when we have one of these large networks, can we say what is the effective dimension of space to which it corresponds? Well, that's actually a pretty easy thing to answer. I mean, these are just different renderings of a particular network. But let's just say we can have a test for the dimension of a network, effective dimension of a network. We just start at a point and we start growing a larger and larger region in the network, going graph distance r away from the initial point. So, and then we just count in this sort of geodesic ball in the network, we just count how many nodes do we get to at graph distance r. And we can do that in this case, and the answer will be r squared. We can do that in this case, the answer will be r cubed. And in general, in something we might think of as a d-dimensional manifold, the answer will in general be of order r to the d. So we can do the same thing in one of these networks that we've just grown from these simple rules, and we'll get definite results in many cases for what the effective dimension of the network is. And we can make a sort of plot that shows how the effective dimension, that the flatness of this is representing the fact that the effective dimension of that object is about 2.7. And you know, if we do the same thing, for example, for that flat thing there, we'll find the effective dimension of that is 2. And we could do it for, let's see, there's a nice fractal one. We can do it for that. Its effective dimension is the standard Hausdorff dimension of that thing. Okay, so one of the things that we learn is we can sort of measure a property of these networks when they get big in terms of dimension. We can also measure curvature. Here are some things which, when we look at them, they seem like they might be curved. Well, curvature, we can also just look at in terms of the volume of this geodesic ball. You know, if we draw a circle on a sphere, then the area of the circle isn't exactly pi r squared. It's pi r squared with a correction term of order r squared over a squared, where a is the radius of the big sphere. And we can capture that same thing in these systems. Here's this particular thing with curvature. It has effective dimension close to 2, but it has some variation in the volume of the geodesic ball that represents the curvature. And it turns out the actual formula for that deviation is proportional in general to the Ricci scalar of the Ricci scalar curvature of the effective manifold that's grown from the large scale limit of these systems. Well, that's kind of an interesting thing because the Ricci scalar is something which begins to be like the kinds of things that appear in the Einstein equations. We can do things like we can look at GD6 in these systems. We know that GD6 on positive versus negative curvature have different divergence and so on. We can look at GD6 here. We can look at the divergence of GD6. We can use that as another measurement of the effective curvature of these systems. Okay, so when we do that, we can, it's a little bit more work to understand how this all works, but in the end, what we'll be able to show is that the effective behavior of these large scale networks corresponds to the Einstein equations. Well, let me show you a little bit more detail here. So let's say we're looking at one of these updates and we say, this is, as I said, there are many possible places where those updates could be done. So here we're just applying one update at a time. And these could be applied in many different orders, but that's one particular order of applying these updates. This is a multi-way system that represents all possible orders in which those updates could be applied, giving a variety of different kinds of structures. But one important thing is often there'll be a divergence because there might be two ways that this thing could be updated and it leads to two different results. But there can also be a convergence. There can also be a merging of two things where two different states merge to the same state. And if we continue going with this multi-way graph, we'll get something more like this. Okay, so a very important property of multi-way graphs. And by the way, we can look at multi-way systems in simpler cases of things like string substitution systems, as well as in things like hypergraph rewriting systems. So this is a string substitution system, and we're asking, and we're looking at what happens when we apply some, I think we were applying this particular rule here. Okay, so important feature here is that every branch has a corresponding merge, happens to occur after one step in this case. So that means that even though there is kind of a divergence in what's going on here, even though there are many things that could happen, there is also convergence. And this property is related to a property that's long been studied in term rewriting systems, variously called confluence, the Church-Rosser property, various other kinds of things. For various reasons, we have a slight generalization of this, so we call it causal invariance. Causal invariance basically is the statement that anytime there's a branch, there will be a corresponding merge. And where are we familiar with things like this? Well, when we do kind of elementary algebra, we have some expression, we're multiplying it out. We say there are all these parenthesized pieces. We could say, well, we could choose to multiply out these two parenthesized pieces, and later on we can multiply out these ones, but it doesn't matter what order we multiply these things in, we'll always get the same answer. And that's what's going on in these systems. Let's see if I have another example here. Let's see if this is an example. No, that's what's going on in these systems, is that we're always getting, even though, so this is the case where we're just looking at a rule that interchanges BA and turns it into AB. So it's a sorting rule. And if you look here, what's happening is there are many different ways we could do the sort, but in the end, we'll end up with the same sorted result, just like we'd end up with the same result if we do algebra in different orders. And this property of causal invariance is an important property that will be critical to what we're talking about. Now, by the way, in this picture, what I'm showing is I'm showing these states, but I'm also showing the events that are the updating events that go between these states. Okay, so what I can now do is to ask, what are the causal relationships between these updating events? In other words, which updating event had to have happened to provide the inputs for the next updating event? So there's that. This shows the causal relationships between those updating events. It shows which event has to have happened before which event for you to be able to go on. And from that, we can build this causal graph where the little dots represent updating events and the edges represent their causal relationships. Okay, so causal invariance implies that okay, so well, let me take an example here. So let's say we're looking at the updating rule. This is showing on a particular string, this is showing a particular way to make updates on that string, particular choice of which updating events occur when. Here's a different choice of which updating events occur when. Notice that in both cases we get the same answer. It took more steps to get that answer in this case than it did in this case. But the important thing is that in all these cases, the network of causal relationships is always the same. These graphs are always isomorphic. Their details are different, but the graph overall, the causal graph is always the same. We can make different detailed choices of when updating events happen, but the causal graph we get is always the same. And that's a crucial fact because that's what basically gives us relativity. So how does that work? Well, we can imagine that we're looking at some very simple case where we have a bunch of updating events, and this is the network of causal relationships between those updating events. If this was our universe and we existed as observers in this universe, we might say, let's make sense of what's going on in this universe. Let's define what counts as a particular moment in time in the evolution of this universe. We might essentially foliate this structure by saying, this is a particular moment in time, this is the next moment in time, and so on. And that this particular foliation in a cellular automaton, you'd be having only this one possible foliation. But what you can do in these systems is you can say, in this causal graph, you can say, let's consider, okay, there's an observer who's sort of traveling at zero velocity, just going straight down the system. That's an observer traveling who is sort of sampling the system, traveling across the system. But what we can do with that observer is we can say, what would that observer do? How would that observer sort of rearrange the system so that they could make their foliations of time be flat? And this is what you would get. And so this is, notice, the same causal graph, but it's differently arranged. And it is that same causal graph, but different arrangement that basically is special relativity. And in fact, you can see in these systems, let's see if I have an example here. Yeah, so this is essentially the rest frame version of how you would sample that string updating system. This is what would happen if you sample the string updating system with a foliation that is tipped. And notice that what you see is that the result is the same. That's a consequence of causal invariance, but it takes more steps to get to that result. Well, what does that remind you of? That might remind you of time dilation and special relativity, and this is exactly the same phenomenon. This is time dilation in the way that it works in special relativity. And in our models with networks and so on, that is exactly how time dilation and Lorentz invariance and so on arise. Well, we can get fancier. In these actual systems, the causal graphs and their foliations are more complicated, but this is basically how things work. What we can do, a consequence of causal invariance is the following thing. So with cellular automata, okay, so basically what happens is continuum space emerges from these discrete atoms of space in sort of the same kind of way that continuous fluid behavior, fluid mechanics arises from the sort of discrete molecular dynamics, the limiting behavior of discrete molecular dynamics in a fluid. And some of you may know that ages ago I worked out this way of taking two-dimensional cellular automata and having them, showing that they limited to the continuum Navier-Stokes equations when you had the right underlying structure for rules in the cellular automaton. Well, that derivation is actually bizarrely similar to the derivation that we now can do of the Einstein equations in these systems. Essentially what's happening is at the lowest level, there are all these sort of atoms of space bouncing around. But when we look on a large scale and we look at this sort of effective continuum behavior here, we find out that it corresponds to the Einstein equations. In fact, the things we need are computational irreducibility, leading to effective underlying randomness, just like the molecular chaos assumption in molecular dynamics. We need the fact that the universe has a finite limiting dimension, which might not be true, but as soon as you say there is underlying computational irreducibility and the universe has finite limiting dimension, and you assume that at least as far as observers are concerned, the universe is causal invariant, then it follows from those three things that the large-scale behavior of space-time follows the Einstein equations, which is a rather remarkable result. By the way, I might say, I mentioned the second law of thermodynamics. I might say that I think it's now I sort of fairly clearly understand that the second law of thermodynamics is kind of a consequence of computational irreducibility. It's kind of the fact that even when you have simple initial conditions for a system, the actual dynamics of the system sufficiently encrypts those initial conditions that for a computationally bounded observer who is doing coarse graining in a computationally bounded way, you can't invert that process and see that it came from simple initial conditions, and therefore you attribute it, you say that it has a higher entropy, and that's kind of the origin of the second law of thermodynamics. And somebody should dot the I's and cross the T's of that derivation, but that's how the second law works. But in any case, very much the same kind of arguments are needed to derive the Einstein equations. Now, if you, in the simplest way of setting things up, you derive the vacuum Einstein equations. Then the question is, what is matter in these? And I mentioned that matter is kind of this large scale, these structures that exist on top of this network, that the network represents everything, space and matter. But you want to kind of tease apart what counts as matter and what counts as space. And it turns out there's a sort of bulk way to start doing that. And the bulk way to start doing that is to identify what energy is in these causal graphs. And it is remarkably simple. I never thought it would be this simple. Energy is simply the flux of causal edges through space-like hypersurfaces. These horizontal slices that represent successive moments in time can be thought of relativistically as space-like hypersurfaces. And you're literally looking at the density of causal edges slicing through these space-like hypersurfaces. What's the interpretation of that? In the network, these causal edges represent activity in the network. So essentially what it's saying is that energy corresponds to sort of time future directed activity in the network. And momentum corresponds to the flux of causal edges through time-like surfaces. And then another thing which is rather remarkable, because it's not something that comes out in the standard derivation of relativity, is the fact that energy momentum transforms in the same way as space and time under relativistic transformations. And that's a consequence of this model. But one of the things then is that we're deriving essentially we're saying that the energy is associated with the flux of causal edges. And in the full Einstein equations, where we have, you know, a space-time curvature on one side and an energy momentum tensor on the other side, this is now saying that we can derive the whole thing, and we can explain how geodesics in space-time are essentially deflected by the presence of energy, by the presence of this higher density of causal edges in the system. And that's more or less how the full Einstein equations get derived. There are all kinds of things we can do with the Einstein equations. This is an example of a cosmological event horizon. We can study black holes and so on. We can get, this is a separation in the causal graph. This is a causal, essentially an event horizon. We can get black hole event horizons. We can get space-like singularities, time-like singularities, all these kinds of things. We can study those types of things in these models. We can also think about things like the earliest moments of the universe and the idea that the universe might start infinite dimensional and sort of gradually cool down to the point where it has the 3 dimensions that we observe today. Okay, so that's a little bit on kind of the derivation of large-scale structure of space-time from these models. The other big thing is quantum mechanics. And one important feature of these models is quantum mechanics is not just an afterthought. Quantum mechanics is an inevitable feature of these models. There's simply no way to have, so sort of the difference between classical mechanics and quantum mechanics. In classical mechanics, definite things always happen. You throw a ball, there's a definite trajectory defined by Newton's equations or whatever for the ball. In quantum mechanics, you imagine that there's a diversity of different paths that could be followed, and you merely work out probabilities of different outcomes and so on. Well, in these models, the different possible underlying rewriting processes correspond to necessarily exploring many different paths. And so this is this kind of a string analog of one of our systems where you're seeing all those different paths. Okay, so maybe I shouldn't go into this in too much detail, but there's a question of sort of how quantum mechanics then works. And there are questions about, oh, I don't know, we could pick almost anything. We can pick quantum measurement. Quantum measurement is all about the way that you make reference frames. This is an example of a typical quantum measurement where you're essentially making a coordinate singularity in the foliation in the coordinate system, coordinatization of this multi-way graph. and that's kind of what corresponds to doing a measurement. In real cases, these things get a bit more complicated. This is an example of something more like what happens in a quantum computer, where you're kind of trying to essentially freeze time in more or less the same way that you freeze time with a black hole in space-time. This is kind of freezing time in branchial space, and that's what corresponds to a qubit. I mentioned the correspondence of if you take a slice through this multi-way graph, you get this kind of notion of branchial space, where these different nodes in this branchial graph correspond to different quantum states, and this is a map of entanglements between them. You can start understanding things like the uncertainty principle is the analog of basically curvature in branchial space. In physical space, when you sort of have two quantities, you go in this direction, you go in that direction, you ask, do these quantities commute? What happens when you do parallel transport around a rectangle? Does the thing close or not? The non-closure of that in physical space is associated with curvature of space. The non-closure of that in branchial space is associated with non-zero commutators of quantum operators, and that gives you the uncertainty principle. And so you can explore lots and lots of different quantum phenomena. Actually, there's a nice example. Let's see. This was really cool. This was not an expected thing that this would be so unbelievably easy. But we just got, let's see if I can pull it up. We just got the double slit experiment to work. And it turns out to be just vastly easier than you can possibly imagine. And you can do it in terms of, purely in terms of string multi-way systems. You can derive the standard interference. And I should explain that one of the things that happens, which is another little bit of a wrong turn that was taken in the early history of quantum mechanics. And people say, oh, quantum amplitudes are complex numbers. Well, that's nice, but like packaging space and time together, it's actually a mistake. The magnitude of the quantum amplitude comes from a different place than the phase of the quantum amplitude. The magnitude of the quantum amplitude in these multi-way graphs comes from path weights associated with the number of possible ways to get to a particular place in essentially branchial space. But the place in branchial space you go corresponds to the phase of the quantum amplitude. So having said that, you can kind of begin to see why the Feynman path integral might have something to do with the Einstein equations, because I'm explaining that the phase of the quantum amplitude is associated with your position in branchial space. So imagine that you're exploring down one of these multi-way graphs. You're exploring down here, and the question is, and you're going down a geodesic. Let me see if I got one of those. I don't think I have one here. You're going down, whoops, wrong picture. You're going down a geodesic here. You're following down a path here. And the question is, what makes that geodesic deviate? And what is the significance of the deviation of that geodesic? Well, the significance of the deviation is you'll wind up at a different place in branchial space, i.e. you'll end up with a quantum amplitude with a different phase. So if you remember the path integral, it is a phase, e to the I s over h bar. So that phase is the result of the deflection of a geodesic in this multi-way system in branchial space. And then you can ask, well, what's the amount of that deflection? Well, the amount of that deflection turns out to depend on essentially the energy, the number of causal edges that exist in this multi-way graph, or actually in the multi-way causal graph. Okay, so what's that S in the path integral? That's the action. The action is essentially the divergence of the number of causal edges in a region of this graph, of this multi-way causal graph. It's just the sort of relativistically invariant version of something like energy momentum. So that's kind of how, that's sort of a sketch of how the path integral comes about from a system like this. It's because just as there's a deviation as associated with energy in physical space, so also there's a deviation of this path in branchial space, which corresponds to quantum phase, which gives you the path integral, basically. So that's to me is just an amazingly elegant thing that those two quantities are sort of the same kind of thing. By the way, when you, if you're into modern physics and things, and you know about ADS-CFT correspondence, it's pretty certain that that correspondence between that the sort of correspondence between those things is related to that. And actually, more to the point, if we look at the multi-way causal graph, that there's a projection of the multi-way causal graph onto physical space, and there's a projection onto branchial space. And those correspond to the two sides of the ADS-CFT correspondence. And when you're looking at a black hole, you get to see kind of things like the physical event, the causal event horizon, and there's a branchial event horizon that also exists, and things about that seem to resolve the black hole information paradox and so on. Well, there are things to say about, gosh, lots of things to say about this. But in any case, I think the sort of the takeaway here is there's another very simple kind of system to study, and it corresponds to these a system unlike cellular automata, which have a built-in notion of space and time. These are systems in which there's no built-in notion of space and time, but those are just built by the system itself, and we can explore the consequences of that. Now, you know, this project is off to a really good start, actually. We just did our annual summer school, and we generated lots and lots of projects about which are about to turn into papers and things, studying, I don't know, local gauge invariance in these systems, and studying, well, there's CPT invariance, all the various things that we're used to in physics, we can study in the context of these models. Turns out that these models are also relevant even beyond physics. I'll mention one thing here. So one of the questions is, when we look at this model and we say, let's imagine that we have successfully found a rule that reproduces our universe. Then we have this bizarre question, why this rule and not another rule? And it's sort of a Copernican moment, because it's like, you know, pre-Copernicus, like the Earth is at the center of the universe, we're very, very special. Post-Copernicus, it's kind of more like, you know, we are just some random planet in a random corner of a random galaxy in the universe. Well, if we find the rule for our universe and it's a simple rule, we might say, gosh, that's amazing because that means we're special again. Well, it turns out that what we realized is that that doesn't have to be that way. Instead, I've talked about how, it turns out one can be essentially making a system like this run all possible rules. So I've talked about how at every step we might have a sort of a selection of, we might say there are many possible places where a particular rule could be applied, but let's say that not only do we apply the rule in all possible places to make a multi-way system that way, we also apply all possible rules. We make what we can call a rulial multi-way system, a multi-way system where all possible rules are being used. Okay, so let's look at what that leads to. Well, we can look at rulial multi-way systems, even in the case of something like Turing machines. Here's a typical deterministic Turing machine. There are its rules, there's what it does. But now we can say, let's make a multi-way system for Turing machines, where we say, here's a non-deterministic Turing machine, and we're showing the various different paths for the different outcomes that could occur in the Turing machine. But now we can say, let's consider the case of all possible Turing machine rules. Let's make a rulial multi-way graph for Turing machines. So we're starting off from the blank tape here, and every edge here corresponds to a particular possible rule to be applied to the Turing machine. So we can do this, we can look at all possible rules, and we get this thing that is essentially the rulial space, or the rulial multi-way graph of Turing machines. So this thing here, this is just the beginning, this is the first few steps for the simplest kinds of Turing machines, but this is the beginning of a graph that represents sort of all possible Turing machines evolving in all possible ways. And so we might say, well, what can we say about this? Well, it turns out we can say all kinds of things. We can say that structure produces, corresponds to a group. We can study its various properties. These are causal graphs for Turing machines. But one of the things that we can do, those are the analog of branchial graphs in rulial space. Here's an example. This is, so in a sense, this rulial multi-way graph is the extreme non-deterministic Turing machine, because it has all possible rules in it. But any particular deterministic Turing machine is just a single path here. So one question we can ask is, how does the set of all possible deterministic Turing machines correspond to the space of possible non-deterministic Turing machines? And that's the red region as compared to the gray graph here. And this particular picture is telling us things about the comparison between non-deterministic computation and deterministic computation. And it's beginning to give us a way to kind of geometrize the P versus NP question by representing the space of all possible Turing machines in a geometrical way. And as I mentioned before, one of the things that is fun is you can do that for cellular automata. There is the Rullial multi-way graph for cellular automata, for elementary cellular automata, has all kinds of weird structure still to be explored, that's the kind of thing we can look at. By the way, I should also say that these things like multi-way graphs have all kinds of significance for things far beyond physics. They're also, it looks like we can make kind of a new approach to thinking about distributed computing, in which we're normally in distributed computing, you're always obsessed with avoiding things like race conditions, which are essentially the branch pairs of our multi-way graphs. They're places where there's an ambiguity in what could happen. But in a sense, the theory that we're developing here is a theory that allows us to sort of deal with ambiguity in bulk. And I think that's going to be really important in distributed computing in the future, because it allows one to sort of think about programming in a certain reference frame, much as we're thinking about physics in a certain reference frame here. We also have some ideas about making models for biological evolution using multi-way graphs. As yet, that's still undeveloped. A thing that we've just been working on the last few weeks is using multi-way graphs and using this kind of theory as a way to understand mathematics, and particularly metamathematics. And to just show you an example of how that might work, in NKS, I talk a bunch about sort of foundations of mathematics. And the thing to realize is that, you know, here are the axioms of mathematics as it's actually practiced. It's only about 2 pages of axioms. The way we use those axioms is we make proofs. And the proofs basically are like paths through multi-way systems. This says, given a particular expression, apply the axiom in just the right way to end up with some other expression to prove that those 2 expressions are equal. And so, in a sense, when we make proofs, what we're doing is we're finding particular paths through multi-way graphs. And so, in a sense, you can think of the space of all possible, the kind of metamathematical space as being a big multi-way graph, much as we can think about physical space, or at least the space of quantum states, as being formed from a big multi-way graph. And so the thing that's kind of a recent interest of mine is an attempt to understand what is the dynamics of mathematics, so to speak, in metamathematical space. And so, for example, a minimal model of a mathematician is someone who follows a geodesic in metamathematical space, always finding the shortest proofs of theorems. And you can kind of ask what happens when you try to do that, and what happens when you build up information about previous theorems and so on. And it turns out there are foundational axioms in mathematics, essentially the extensionality axiom of set theory, or the univalence axiom of univalent foundations in homotopy type theory and so on, that correspond to an idea in mathematics, which is when you prove that 2 things are equal, for example, you can just keep the theorem that says those 2 things are equal and throw away the proof and not worry about the proof. And those axioms are basically telling you that you can do that. And as soon as you do that, you essentially produce the doing of that is extremely similar to the causal invariance property in these models of physics. And as soon as you do that, you have all kinds of consequences. And so an example of a consequence is that you can do something very bizarre. You can start thinking about deriving the Einstein equations in metamathematical space, essentially deriving equations that describe the motion of mathematicians in some sense in metamathematical space. And one of the more bizarre conclusions, very recent conclusion, is that it seems that there is, as you accumulate theorems, you inevitably build up sufficient mass, sufficient energy, that you force the singularity theorems of general relativity to apply, and you essentially end up with singularities in metamathematical space, or essentially black holes in metamathematical space. And that leads to essentially the theories becoming effectively decidable. Once you add enough theorems in a theory, the things that you explore end up being sort of closed-ended and decidable. And one of the things that for me has always been a huge mystery is when we look in the computational universe and we just start doing computer experiments, an awful lot of the things that we ask about are, we are immediately thrown into undecidability. And one of the things that's been sort of that's been a big surprise in mathematics is undecidability happens, but it's not all over the place. There's still plenty of mathematics you can do. Okay, so let me make a sort of a key point here, which is in the theory of physics, one of the super surprising things is that our theory of physics is not blocked by computational by computational irreducibility and by undecidability. It could be the case, and I thought this was what was going to happen, that we can make up this rule for understanding how a universe works. We can trace it for a small number of steps that might correspond to 10 to the minus 100 seconds in the history of the universe, but that's as far as we can get. And computational irreducibility basically prevents us from going and finding out what happened after 14 billion years and so on. But the really surprising thing is that, in fact, it turns out that we're able to see certain computationally reducible features of a wide class of computationally irreducible universe models. And what are those computationally irreducible features? They are basically the triumphs of 20th century physics. They're general relativity and quantum mechanics. Those are computationally reducible slices of this generally completely irreducible structure that is the evolution of the universe according to these kinds of rules. So one of the big surprises is that sort of floating on top of all this irreducibility is this layer of reducibility. And one of the things we realized is that because the reason we see that is because we are essentially computationally bounded observers. And we're kind of forced into seeing that layer of reducibility. Now, one of the things that's important about that is there are many other kinds of computationally bounded observers. In a sense, there are many other foliations of Rullial space that also describe our universe. So we think we have a description of the universe in terms of space and time and particles and all this kind of thing, but there are utterly incoherent descriptions of the universe that can also be given that are describing, in a sense, the same universe, but describing it in utterly different ways. And, I always used to think that, alien intelligences, at least they share the same physics, but they don't, because they can take a completely incoherent view of kind of what's important in physics. And, if you sort of abstract physics away from our senses and our way of understanding the world, you get something quite different. So, okay. So the same, by the way, and thinking about the analog of that in mathematics is thinking about different kinds of axiom systems as sort of different ways to explore metamathematical space. And you can think about the space of all possible axiom systems. I looked at that a bit in NKS, which is this Rullial multi-way graph in metamathematical space. And that thing corresponds to this infinity groupoid, which I mentioned earlier. So, but in any case, I was just to finish the thought about kind of the physicalization of metamathematics. What that gives you is things like this. It sort of explains why one hasn't seen more undecidability. It's because once theories get developed to a certain point, they are sort of forced to undergo gravitational collapse in metamathematical space. And they are forced to essentially get to the point where theorems can be proved, and where, in a sense, eventually one will have mined out that whole area. One will have sort of gotten to the singularity in that particular part of metamathematical space. And that's, in a sense, the difference between the mathematical approach to exploring things and the computational experiment approach to exploring things. In the computational experiment approach, you're not following just these sort of geodesics in metamathematical space. You're going off in all these different prongs in different directions, and that's why you end up seeing much more undecidability and so on. I mean, I would say that sort of tactically in the evolution of, for example, our fundamental theory of physics now, one of the things that's quite important is that there is a lot that can be studied in a computationally reducible way. One of the things that I think was a frustration back when I was first studying cellular automata in the early 1980s, a number of very good mathematicians got involved, and they who've been involved in things like dynamical systems theory and so on, and they immediately thought, we've got these very powerful tools. We're going to be able to crack cellular automata just like we could crack iterative maps and things like that. And they tried doing it and they couldn't really get anywhere. And essentially what was happening was that they were hitting this sort of wall of computational irreducibility almost immediately. There wasn't a layer of reducibility on top of that. And what we're seeing in this model of physics is we have discovered from 20th century physics, basically, that there are these layers of computational reducibility that sit on top of this bedrock of computational irreducibility. And that's the thing that, that a lot of what we're doing in this fundamental theory of physics is about. It's also what is allowing us to make connections to many other areas. One of the remarkable things is that I had thought that our sort of approach to fundamental theory of physics would just be quite completely incompatible with, you know, string theory, conformal field theories, spin networks, all these kinds of things. But actually it isn't true. An awful lot of these things are turning out to be actually, in some appropriate limits, equivalent to the theory we're studying. I kind of view it as a little bit analogous to what happened with Turing machines. There had been things like combinators, lambda calculus, post-canonical systems, later register machines, things like this, all these different models. And you know, by the things like combinators and Gödel's theorem and general recursive functions and so on, it hadn't been clear what kinds of things those were and whether they were much connected. But as soon as you have the sort of concreteness of Turing machines, you can see that all these things can actually connect into that. I think that's what we're kind of seeing with these models that we have now, that they are a sort of concretification of a lot of abstract ideas that have arisen in mathematical physics, which is kind of a neat thing because it allows one to take the methods and results and so on from those different areas of mathematical physics and bring them to bear on studying our sort of fundamental theory of physics. But I think that one of the things I'll probably stop in a moment here, and I'm really happy to try and answer questions if I can. I think one of the things that this has made me think very recently is, okay, so if I look at something like cellular automata, we now know that for these other systems, there's this layer of computational reducibility that sits on top of these systems. What might that layer be like for something like cellular automata? Now, remember that in order to find that layer, we are making use of the fact that we have sort of sensorially detected things like space and time in the universe. In other words, you know, it could have been the case that in our existence in the universe, we would never be able to predict what was going to happen next. Everything would seem computationally irreducible to us. But the fact is, it's sort of a critical fact about our existence that we are able to make use of computational reducibility to the point where we can have some expectation about what's going to happen next. We can deduce laws of physics, things like that. But to do that, we are keying into certain sensory features of the physical universe. And so a question that sort of I think is a kind of a big challenge question for thinking about things like cellular automata is, what is the analogous? Is there some way to think about things? Is there a physics of cellular automata effectively, as there is a physics of the physical universe, a physics in which there are sort of computationally reducible things that globally sit on top of the underlying irreducibility of the system? I don't know the answer to that. My guess is that while one feature of computational irreducibility is that it's inevitable that whenever a system is computationally irreducible, there will always be an infinite number of pockets of reducibility. What those and different sort of sensory approaches will correspond to different, exploring different pockets. But the question is, what are the general such pockets that exist for things like cellular automata? Well, I should probably stop there, but I just want to sort of re-emphasize my point that you know, what you guys are doing is an important thing to do. You know, you're studying the basic science of the computational universe. It's the kind of, it is the pure mathematics, it is the pure science which underlies all these computational X fields that are emerging, that underlies kind of the future of much of science, and it should be treated as seriously, as aesthetically, and as aggressively, so to speak, as pure mathematics has been treated. We don't yet have this as a clear sort of field of science. I consider it one of my mistakes in the 1980s when I was kind of helping to develop sort of what's become complexity theory, that I didn't really slice off the pure science of the computational universe from its applications. Those things got mixed together in a way that didn't happen in mathematics. In mathematics, we have pure mathematics. It's sort of separate from the applications of mathematics and even from the field of applied mathematics. And so one of our challenges going forward, I think, is to make this kind of pure study of the computational universe into a meaningful and valid field of science on its own. You know, my journal, which Hector edits, Complex Systems, it was an example of the first journal that really concentrated or tried to concentrate on this kind of direction, but there's much more to be done in these areas. And I think that is the thing that we should be looking forward to and pushing for and trying to organize, is how do we organize the basic science of the computational universe? Now, I do think that our physics project will probably help, because our physics project basically says, look, if you want to study physics, it lives on top of this study of the computational universe. This is kind of a killer app use case, so to speak, for the computational paradigm and the abstract study of the computational universe. And I hope that as it evolves and as we get more people involved in it and so on, that it will start to emerge in those directions. And I think I'm certainly interested in what I can do to help sort of further the organizational structure of kind of the basic science of the computational universe. And as I say, it's terrific to see you guys in this conference and so on concentrating on that. There just needs to be as much of this as there is of pure mathematics, actually much more so, because this is a much broader and more important direction than pure mathematics, and will inform, there will be many more computational X fields than there ever have been mathematical X fields. But this is the basic science that's needed to make those fields go. And this is something that I think we should be pleased to be involved in, and that we should try to make sure actually lives and prospers in the world as it is today. All right, I should stop there. Let me go and try and answer some questions here. All right. So there's a question from Kevin Parrott